Hello, I'm here to talk to you today about specifics of specific energy. It just rolls right off the tongue. It's a very catchy title. I'm sure that's why you clicked on this video. My name is Kerry Troy. I'm from Purdue University. The focus today is on gradually varied open channel flow in constant width rectangular channels. I know that's a mouthful, but basically we're talking about flow where the depth is changing as you go downstream. The flow is gradually varied, which means that if it's subcritical, it's going to stay subcritical. If it's supercritical, it's going to stay supercritical, but the depth is changing with distance downstream. We have a constant width channel, so this variable B is the channel width. It's rectangular, so the variables B and Q, the flow rate and the channel width, are not changing with distance downstream, and that's an important sort of caveat to everything I'll tell you today. The other thing that we have is a channel where the bottom is changing in elevation. And so what I'm showing you here is a bottom that has a constant slope, so some slope S0. But what we'll talk about today is general to any sort of bottom variation, provided it's fairly gradual. So it doesn't have to be a constant slope. It can be, something more like a hill or a depression. We'll look at some examples later, and you'll see that. Okay. Specific energy. So this is kind of the key concept of today's lecture. A couple of variables that we need to get used to with specific energy. One is the flow depth. We're going to call that Y. The other one is the elevation of the channel bottom relative to some datum. That's called Z. Okay, so we will learn more about Z in a second. But the flow depth, Y, is an important variable, maybe the most important variable once you have a given flow rate and channel width. Okay, so again, those are fixed for these problems. So specific energy is kind of like the Bernoulli equation, where you had energy related to pressure, potential energy, and then kinetic energy. Okay, so specific energy for open channel flow is denoted by the letter capital E, and it's defined as the depth plus v squared over 2g. And this v that we're using here is the cross-sectional average velocity. It's equal to q over a, and for a rectangular channel that would just be the same as q over by. Okay, but the idea here is that the energy of the flow has this depth term in here, and you might say, well, where's the pressure? Bernoulli had this pressure term. Well, it's related to the fact that open channel flow, again, by definition, is not pressurized. And also in open channel flow, we typically have, or at least assume, hydrostatic pressure distributions. And so once you fix the depth of the flow, that also fixes the pressure. And mathematically, it turns out that both the pressure and the elevation relative to the channel bottom are sort of embedded into this Y term here. Okay, so think about this one as pressure and elevation above the channel bottom. The other term, of course, is kinetic energy. That's pretty familiar from the Bernoulli equation, right? V squared over 2g. The units, of course, of this equation or this energy are kind of like head, so it's either in feet or meters depending on your unit system. Okay, but that's a definition of specific energy. And the one thing to note is that, well, let's see. Once you fix the channel, once you fix the depth of flow, you could calculate this v squared over 2g term, right? It's given by q divided by by. So these two terms are not actually independent of one another, okay? And the way this plays out is in something called the specific energy curve. And the way that you would think about making this curve would be in Excel, where you have some depths. So maybe you have a column of depths. Let's just start with one depth. And then you have another column which is equal to your specific energy, and that would be simply equal to y plus v squared over 2g. And the v would simply be equal to your q over by. Okay? And then you could do this for a bunch of different depths. And if you calculated that and plotted it, graphed it, it would look like this. Okay? It looks sort of like a C-shaped curve. Importantly, the y-axis, not surprisingly, is the variable y, and the x-axis is actually the energy E, specific energy E. And the curve is always going to look like this sort of C shape. This line here is a line of 1 to 1, and the turnaround point here is actually occurring at the critical depth. So it's a little bit strange that you have y on the y-axis. I guess maybe not, given the name. It is called y after all. But as you go up on this axis, you have deep flows, and as you go down on this axis, you're thinking about shallower flows. And really our measure of deep or shallow, as usual, is the critical depth. And so related to that is regions of the curve that are above the critical depth are subcritical and regions below are supercritical. And what's going to happen with the specific energy is that energy will be conserved. Even if we have head loss, we'll be able to account for that. And we are going to be sliding along one portion of the curve or another. And again, we're remaining subcritical, gradually varied flow, or we are remaining supercritical, so we're just sliding along from one location in the channel to the other, upstream to downstream. We're either going left or right, and we're staying on one of these two limbs. If we had rapidly varied flow, we would be either doing a hydraulic jump, where we go from super to sub very rapidly, or if we had flow over a critical point, we would be going around that corner very quickly. But today we're just talking about problems where you stay along one limb or the other. So all that to say that you end up staying on the curve for these problems, and there's some comfort in that. A couple of things to note, or other things to note. One is that if you have a given flow depth, that will exactly determine your energy. We already did that calculation. That was the sort of the making of this curve, right? On the flip side, if you have an energy, there's actually three possible depths that could have that same energy. So it's very confusing. But if you knew some energy, you wouldn't know whether the correct depth was this one or this one. And then there's actually mathematically a third root. So it makes it very confusing in terms of going from energy to depth. Okay, so that's kind of why we use this diagram. You'll see how that works. All right, so like the Bernoulli equation where we had, or pipe flow energy equation, where we were equating the energy at one location to the energy at another, we need a statement of the conservation of energy. So the statement of conservation of specific energy looks like this. So, or you might think it would look like this, right? Now let's say that we have some Z1 here and a Y1, and then the channel changes elevation. We have a Z2 and a Y2. And if we wanted to conserve energy from cross-section 1 to 2, we might say that E1 is equal to E2. And just for a good measure, we'll throw in head loss because we know that a real channel will probably have friction, right? So that's not quite right, okay? And the reason is that if you do that, you're not accounting for the potential energy change related to the bottom elevation change. So the full conservation of energy, specific energy equation looks like this, where you have E1 plus C1 is equal to E2 plus C2 plus head loss, okay? And so this is kind of our engine for solving these problems in much the way that the Bernoulli equation or the pipe flow energy equation allowed us to go from upstream to downstream or vice versa, okay? And this head loss term is related to energy dissipation between the two cross sections, sometimes due to the friction of the channel and other times due to other things. All right. So let's just dive right in and solve some problems here. So a typical problem would look like this, where you know the channel bottom elevation changes. So your channel is changing elevation from Z1 to Z2. We're going to think about a rising channel first, and we'll do a falling channel in a second. We are typically given the upstream depth, or one of the depths. Let's just assume we're given the upstream depth for this one. And what we're trying to figure out is what is the new depth downstream, okay? So Y2 is equal to what, okay? And our energy equation is this one here. I'm going to use a slightly different version here. And the version that I'm going to use is a rearrangement of that one. It's going to look like this, where we have E2 is equal to E1, and then I'm going to write it in this way, minus Z2 minus Z1 minus head loss, okay? And for most of the problems today, we're just going to neglect head loss, but I will talk about how that affects the solutions toward the end, okay? So let's forget about the head loss for now, okay? We'll assume a frictionless channel. So how do we use this diagram, okay? Well, the way you use it is you start with what you know, which is Y1, okay? So we're going to start, let's say we have subcritical flow, right? So we would expect to be up here above the critical depth. Let's say our Y1 was here. That would be given by whatever the numbers were for the problem. We know that we have a specific energy at the number one cross section that would be corresponding to this value, right? We walk over to the curve and then we walk straight down, and that's our E1, okay? We can calculate that too the same way that I showed you before. Now we need to figure out, are we going to go left or right along this curve up here? So the question is left or right. And the way that it works out is that if you have a positive Z2 minus Z1, so notice that this elevation change here is this distance here is Z2 minus Z1, okay? So if the channel rises, then Z2 minus Z1 is positive, and you end up with a minus of a positive, which means that we're actually going to be reducing our energy from E1, okay? So all that to say that what you do now is you're going to move over to the left because the channel rose. We're going to go over here to E2. The differences in those energies is Z2 minus Z1, okay? And then we're going to walk our way back up to the curve over here, walk our way over here, and pick off our Y2. And literally that's the solution of the problem. So notice, just to recap, Y1 took us to E1, energy equation gets us to E2, walk your way up here, and land on the curve again, and then walk your way over to figure out what the Y2 value is, okay? So this is sort of the graphical way of doing it. Let's do another one. So instead of subcritical flow, let's say we had supercritical flow, okay? So in supercritical flow, we know we are down here. So let's say that we had some Y1 down here. We walk our way over to the curve. We're going to have some E1, and because the channel bottom is rising, again, we have a Z2 minus Z1 is positive. We are going to be doing an E1 minus a positive, so that would push us to the left on the diagram. And I don't quite have a lot of room. I don't have so much room here, but the idea is the same as the previous example. E2 would be over here. The difference would be Z2 minus Z1. And we simply walk our way over here to get to Y2. And so the interesting thing on that one is that the depth of flow changed slightly, it increased slightly, and that is a hallmark of supercritical flow over a rising channel. The depth here will actually increase by a little amount, okay? I forgot to mention in the other one, the previous page, for subcritical flow over a rising channel, the free surface will actually dip down a little bit. So we know that the depth Y2 would go down, right? But it turns out that Z2 plus Y2 actually goes down as well, okay? So anyway, all right, let's do the reverse situation where the channel bottom is falling, okay? And we'll start with subcritical flow again. So let's just pretend that we had some Y1 here. So we would walk our way over to the specific energy diagram here. Our intersection point is there. That would determine our E1. And now we have a situation where Z2 minus Z1 is actually negative, right? So this distance here, this is basically Z2 minus Z1 is negative, okay? And so our energy equation looks like that. Get rid of this stuff here to leave some room. And all that to say that if we employ this equation here, we end up with a minus of a minus. We're going to neglect head loss again, in which case these two minus signs equate to a positive value, and we need to add that elevation change. So the difference here would be Z1 minus Z2, which is positive because Z1 is greater than Z2. And now what we do is we again walk our way up to the curve, and then we would walk our way over to Y2 here. In this case, you can see that the depth has changed, which seems kind of obvious given how things look over here for the number 2 cross section, right? And it actually turns out that for subcritical flow, as the channel bottom falls, the free surface will rise very slightly. The farther you are up here on this limb, as you get to the one-to-one part of this curve up here, you will not notice this rise of the free surface. It's basically, as the farther you get up this one-to-one limb over here, it's kind of like the Mississippi River flowing over a small pothole. The free surface is not going to really acknowledge that pothole, right? But anyway, in theory, it should go up a slight amount as the channel falls, okay? That's for subcritical flow. And then supercritical flow we can do really quickly. Again, we have our energy equation. We have the channel bottom falling, so it's going to be equal to E1 You could write it this way, plus Z1 minus Z2, right? And this is a positive value. So if we're in supercritical flow, we could be over here. This would be our Y1. Walk our way over to the curve, get our E1 over here, and then we're going to move to the right by an amount equal to Z1 minus Z2. Again, we're neglecting head loss. And walk back up here, and we would see that the depth is actually a little bit less for supercritical flow over a falling channel. Okay, and I've tried to sketch that here where this part of the flow is shallower than this part over here. Okay, so the details, how much shallower, will depend a lot on the geometry that you're given, the values of Z1 and Z2. But this is the basic idea, okay? So in summary, the recipe is something like this, where we have our energy equation, E2 and E1. We're going to be given a Y1 value that will put us somewhere along this axis here. We will calculate an E1, and so that calculation can proceed graphically, or you can actually calculate it out. So I'm just going to do a supercritical example here. So step 1 says go from Y1 to E1, which if you do it graphically looks like this. Step 2 is going to be our energy equation to get E2. So depending on what the channel bottom is doing, we will move over by some amount. And this would be the case here. Going to the left is going to be if the channel bottom is rising. And then we're going to get to Y2 for our solution. Okay. So graphically, again, just to reiterate that, sort of the direction that we move goes like this. We go like this. Here, we move one way or the other, and then we pop back up and grab our new depth. Okay, so think about this sort of flow as you're using this diagram. Okay. Just some quick rules of thumb. If the channel bottom rises, you're going to go left when you're doing this energy step over here. If the channel falls, you're going to go right. And one thing about head loss, because of the energy equation, it's always going to push you to the left if you have head loss. You can't have negative head loss. So because of the energy equation where we have E2 is equal to E1 minus Z2 minus C1 minus head loss itself is always positive. And with this negative sign in front of it, you get a negative times a positive. That will always mean that you will be moving to the left on your diagram. Okay, so between E1 and E2, head loss would always push you to the left. Okay, so a couple of questions you can think about. I'm not going to answer them now, but they help you to understand this a little better. If you can explain them, feel free to email me. If the channel bottom falls or rises, will the depth go up and down? And what about the free surface? And like many good questions, the answer really is it depends. And so I'm hoping that you can think about it depends on what. Does head loss make the depth go up or down? And I guess that would be another one where the answer depends. And then a last question is, everyone says water only flows downhill, right? Well, I think we saw a picture there where supercritical flow can actually flow uphill, right? So that's kind of interesting thing about open channel flow, and I think it's maybe based on most of our intuition, which is related to subcritical flow. Most rivers are subcritical, at least in the Midwest where I am. And so supercritical flow is kind of a strange animal where it can actually flow up a bump, up and over, provided the size of the bump isn't too big. Obviously, if it's Mount Everest, it doesn't matter if this flow is supercritical, it's not going to make it over. But these are some study questions, and again, email me if you can't figure out the answers to any of these questions. So that's all I have for this, open channel flow, specifics of specific energy. Hope it's been helpful, and I wish you luck in solving problems in fluid mechanics.